Coming up, Space Selfie.
Satellite launches.
And why a rocket failed.
Plus, we're going to be talking about next generation propulsion as our main topic. Stay tuned. Tomorrow begins right now. And welcome to Tomorrow, episode 8.23 for Saturday, August 8th, 2015. My name is Benjamin Higginbotham. With me, as always, the beautiful, lovely, wonderful, and talented Carrie Ann Higginbotham will be your host for this episode. We have got an amazing interview coming up for you guys. It's going to be about next generation propulsion and beaming microwaves from the ground to get a spacecraft into space to send your payload. It's going to be awesome. You're going to want to stick around for that. But before we get into that, I did want to give a huge shout out to all of the patrons of Tomorrow who've helped to make this specific segment of this episode happen. These are the Tomorrow Premier members. These are people who've contributed $10 or more to this specific episode. If you would like to become a crowdfunder of Tomorrow, you can head on over to patreon.com/TMRO. A huge thank you to everyone who helped to make that happen. All right, we're going to bring in Space Mike in just a moment, but before we do that, we had a launch on July 25th, 7 minutes after midnight, of the Wideband Global SATCOM, or what is it, WGS-7 of a Delta IV rocket. Here you go. It's going to be a fun show.
We have ignition, 2, 1, 0, and liftoff of the United Launch Alliance.
He's excited.
Delta IV rocket carrying the 7th WGS satellite for the United States Air Force.
That's a Delta IV Medium Plus.
SATCOM satellite provides significant
Blah, 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 SATCOM satellite. Delta IV Medium Plus with 4 solid strap-on boosters on the bottom. That's not the heavy configuration. That's kind of down in between. Like I said, that happened July 25th, 7 minutes after the hour. And the WGS satellite will give you, quote, anytime, anywhere, communications infrastructure used by soldiers, ships, aircrafts, and drones. So yeah, there you go. This was deployed 42 minutes into the flight itself. Completed the 30th Delta IV flight and United Launch Alliance 98th successful concurrent mission. So there you go. Pretty awesome launch. WGS-8, the following one after this, is slated to occur next year. It will also be aboard a Delta IV rocket launching from Cape Canaveral, followed by WGS-9 in 2017 and WGS-10 in 2019. And I believe they need 6 of these satellites in their current configuration to run the entire constellation. So you also have a little bit of launch.
Launch news, happening.
Launch haps.
Launchy things. Yeah, there was a Soyuz that launched the second part of the Expedition 44 crew. This was from...
Oh, you can talk about it. It's going to be like 20 seconds before this gets off the pad.
All right, good. So this is at 5:02 p.m. Eastern Daylight Time, or 21:02 UTC, Wednesday, July 22nd, from the Baikonur Cosmodrome in Kazakhstan. This is, of course, on the Russian Soyuz rocket headed to the International Space Station, carrying NASA astronaut Kirill Lindgren, JAXA astronaut Kimya Yui, and Russian Soyuz commander Oleg Kononenko to stay on the ISS for the next 5 months as part of the second portion, like I said, of the Expedition 44. The Soyuz TMA-17M, totally easy names to remember, was originally scheduled for May 26th, but the mission was postponed after a Russian Progress resupply spacecraft malfunctioned on its way to the International Space Station in April. As a result, European Space Agency astronaut Samantha Cristoforetti wrecked one of the longest ever stays in space, the longest ever in space for a female astronaut, 199 days. This was not without some sort of something, though. The spacecraft...
Some sort of something.
I was going to say malfunction. That's the word I want. I was like, something going wrong, but that sounds really ominous. That's what I wanted. The portside solar panel did not deploy when originally directed, but right around the time that Soyuz made contact with the Rasavet docking module, the panel spun free.
Freaky, actually, a little scary.
Yeah, I can
imagine. The other thing that was scary is when I was watching that launch coverage, it takes so long for them to release the vehicle, and it was at night, so the image was overexposed. And, I'm sitting there, and it's like 10 seconds after the engines ignite that they actually release the vehicle and commit it to space. But it was overexposed, and it encapsulated the whole vehicle, and I thought they had lost the vehicle. For like a split second, I'm like, oh my gosh, something's gone wrong on the pad, and then off it goes. I'm like, or not, it's just overexposed. So yeah, there you go. So, oh, I'm sorry. Was that?
No, I mean
All right, cool.
that's all I had. There you
So
go. Done.
let's head on over to Space Mike. Oh, that was a horrible. I'm not even gonna transition using that. I didn't think that through all the way. Let's head on over to Space Mike and talk about some Falcon 9 flight failure modes.
So speaking of things that go wrong sometimes.
Yeah,
There you
no
go.
kidding.
Good.
So we've gotten a lot of new information on the Falcon 9 failure that occurred on June 28th. What happened is that one of the support struts inside of the second stage tank hold up several helium tanks. These helium tanks, as the liquid, specifically the liquid oxygen, is being burned on that second stage, the helium tanks release the pressurized helium that's within them to keep the upper stage pressurized so that they don't lose the pressurization, so that they can have the engine burn at its most nominal and have the most amount of thrust throughout its entire portion of its flight.
Otherwise, it get crushed.
When this
Right? It'd be crushed,
exactly.
right? It'd crush it, it'd suck itself in and be crushed like a Coke can.
Exactly. It'd be like a Coke can down in the deep part of the ocean. Well, and to kind of keep with that analogy, when this strut broke, because helium is lighter or more buoyant than oxygen, that tank just shot up to the top of that upper stage, which is what caused the explosion that we've seen several times. And it turns out that this strut was actually from a supplier whom SpaceX hasn't named yet, which is cool because they would probably get a lot of hate if it was known who they were. But it turns out that they did several tests and found out that lots of the different struts that they've gotten from this supplier weren't living up to the sort of tolerance that they were specified for. And that was about to be about 10,000 pounds that they were supposed to have a tolerance for. This particular strut on this flight failed at 2,000 pounds, and there were several others that were found that failed as well. So SpaceX from this point on is not going to be using those particular struts from that particular supplier anymore, and all of their future struts that they're going to be using on all of their vehicles are going to be individually tested to make sure that they're actually up to spec and can withstand those tolerance levels. And something else that's interesting about this particular mission is that the Dragon capsule actually survived for a while before it actually splashed down and they lost contact with it. Its parachutes did not deploy, but it did have parachutes, obviously. So something that's interesting is SpaceX is going to be adding software to all future Dragon 1 or Dragon Cargo, whatever you want to call it, so that if in the case of an emergency like this, they would be able to deploy the parachutes and save the Dragon capsule and all of the hardware that's on board. So that's kind of a cool thing that they're going to be working on in the future. But as far as when the next Falcon 9 is going to be launching, Elon Musk has said that it won't be any sooner than September. And they haven't given any information as to which one of the particular missions in their now growing backlog would be launched first, if and when they're certified to return to flight. So lots of interesting things that are going on in that particular realm from them, and there's more information that we're getting all the time for this. One other thing I wanted to mention real quickly was that it seemed at first during the initial press releases about this that they would be throwing away all of the other Falcon 9s that are in various stages of production. It turns out that what they're actually going to be doing is just removing all of those struts, testing new struts that are actually up to those tolerance levels, installing those, and continuing on without having to start over from scratch on several of the different Falcon 9s that are in the production line. So that is one good thing that won't be losing a lot of the money or work that's already been done in the coming months. So hopefully it'll be very soon that SpaceX will be returning to flight. So for now, though, I need to turn it back over to Benjamin, who has some interesting news about selfies.
Maybe. Although I think there's a new interesting drinking game of tomorrow. Every time, go back, watch the show again on demand, and every time Mike said strut, take a shot. All right, we do have, here we go. We got a space selfie. Boom, there you go. For whatever reason, I usually read The Verge, and they said this is the first time since the Apollo era that we've had a full shot of the Earth. Yeah, Mike's shaking his head no, and I had to tweet back at him. I'm like, that is so wrong. It's not even, there was a live streaming shot on Dish Network of the entire Earth for years since the Apollo era. So yeah, this is not the first time we had a full shot of the Earth. However, this is the first shot from the Discover spacecraft. This is the first picture that was sent back. This picture was taken July 6th and was released by the White House on July 20th. in conjunction with the 46th anniversary of the Apollo 11 moon landing. And this is at an L1. Discover's parked at L1, or the Lagrange 1 point, which means it's kind of in between the sun and the Earth, and that allows it to get a full shot of the Earth fully, like completely bright all the time. You get basically that shot. Now they're going to start, boom, there you go. Fully bright, all sun, all the time, round. Awesome. No crescent is, I guess, what I'm getting at. Now they're going to be getting a lot more pictures. They're going to start to get a lot more stuff starting, like full surface for pictures starting in September. And they're hoping to start posting those on the NASA website after they download them every 12 to 36 hours. But there was an even more awesome shot that came from Discover. Check this out. This is a video. Well, this is a series of images that they've turned into a video. Yeah, you know what that is in front? That's our moon. Now, if it looks a little bit fake and weird and like there's a weird like little thing on the right-hand side of the moon, that's because there is. The way Discover works is it has different wavelength filters, red, green, blue. You take those wavelengths, you reassemble them back together, and you get one colorful, cohesive image. However, it doesn't grab all of the wavelengths at the same time. So, for example, to grab web, let me try my words this time. It will grab red, right? Then it will wait 30 seconds after it's done processing the red image, and then it will grab green. It'll wait 30 seconds, and then it will grab blue. Well, the moon moved too fast inside of that image, and so what ends up happening is that you get this kind of weird green shifting, which is why you see that weird edge along the outside of that. And that's known. That's what happens when you don't take the picture all at once. So there you go. I thought that was actually an incredibly gorgeous shot coming off of the Discover spacecraft. I forgot to mention it was launched February 11th on a Falcon 9 rocket. All right, heading it back over to you. We had an NTSB, National Transportation and Safety Board finding for the SpaceShipTwo.
Yes.
Those words.
Yep.
Yep.
The National Transportation Safety Board released a video showing the SpaceShipTwo rocket plane drop from its carrier aircraft, ignite its motor, and prematurely engage its braking system just before disintegrating above California's Mojave Desert from October 2014. Investigators concluded Tuesday that the cause of the crash was the early unlocking of SpaceShipTwo's tail feathers and inadequate safety and training measures from Scaled Composites, who is the builder of the suborbital rocket plane. It was unlocked at Mach 0.92 instead of the intended speed of Mach 1.4.
Yeah, that was the shot you just saw, I think, is the one that really made me gasp the most when you saw the whole craft. You know, it looks like the front of the craft is actually tilting back, but really what's happening is the camera is attached to the tail feather, so your perspective is whatever the tail saw.
The system has to be unlocked by Mach 1.8 at the latest, or else the flight is aborted. So the going theory is that the pilot was basically trying to make sure that the flight didn't get aborted and unlocked a little bit too early, which is unfortunate. The wing repositioning placed a lot of force on SpaceShipTwo, which was actually too much to handle. They're calculating it at about B9 Gs, which is just a scary, scary thought. So anyhow, video was released. I'm sure as more details come out, we will keep you updated, but it's just a sad thing all the way around. And the lack of safety and training measures that are coming out of the report are just
large.
Yeah.
So yeah.
Yeah.
Pilots didn't really know. There wasn't enough information that flowed between, I think, the engineering team and the pilots possibly. So that does suck, but they've released their findings, and it does at least give Virgin Galactic kind of steps forward to move towards. Now, of course, this was controlled by Scaled Composites, not Virgin Galactic, and since then, Virgin Galactic has basically taken control of the vehicle. And actually, Space Mike has a fantastic space pod on this. If you go back a couple days, he goes into way more detail than we just went into, kind of what happened with there. So speaking of Space Mike, let's hand it back over to him and talk a little bit about Atlas V, or Atlas V, if you prefer.
Who doesn't know?
Well, Lockheed Martin has gotten a contract to launch the EchoStar 19 communications satellite, which would be providing high-speed internet services to North America. And this launch would not occur before 2016 at the earliest. And it's kind of cool because EchoStar has been part of the whole communications industry since the beginning. I mean, you know, a lot of people think that the first ones, you know, were EchoStar. It was actually Telestar, but I mean, EchoStar has been there since the 60s, so this is really cool. They're now owned by HughesNet, but this is really kind of a historic thing that once again, an EchoStar satellite will be launching on an Atlas rocket, even though it's the Atlas V now. Still going to be a cool thing. So great for Lockheed Martin, and this is not a United Launch Alliance contract. This is a Lockheed Martin contract. So there is that little difference there.
Well,
so,
actually, help me out there. What is the difference? Because if it's an Atlas V, it's going to be launching through ULA, is it not? I mean, it's not going to just be the Lockheed guys, is it?
That's the thing. Like, according to the press release here, this is just a contract through Lockheed Martin. And whenever it is a launch that United Launch Alliance would manage, then both the people that are working for United Launch Alliance, who are from Lockheed Martin and Boeing, would be working on the ground, and the support structure there. And whenever there's just a Lockheed Martin launch, I treat this almost like the way that they treat their government launches. Like, whenever there's a government launch, whether it's flying on a Boeing rocket or a Lockheed rocket, just those employees for those companies are working on that particular launch, and not the United Launch Alliance people. That's the thing. Like, with all the military contracts, it's contracts with Boeing and Lockheed Martin, not United Launch Alliance. So it's just a technical thing there. I don't think that there is necessarily a whole lot of ITAR stuff or anything that is a classified payload on this launch for why they would only want to work with just Lockheed Martin, but I'm just going with the information that they've publicly released.
It's also interesting that the Atlas V has won a commercial launch, right? You think of the Atlas V, you don't really generally think of commercial launches. Same thing with the Delta IV. You think government satellite launches. And so Lockheed or ULA or just Lockheed or however that's going to work out actually got a commercial launch for the vehicle. I should be nice. That came out completely wrong. But they did. I think it shows that they're able at least to reduce their costs and they're being competitive in the industry. I thought that's pretty cool. So yeah, end thought. All right, we're going to take a quick break, and when we come back, we're going to be talking with Dmitriy, who is the CEO and CTO of Escape Dynamics, about a next-generation propulsion system. So stay tuned. We'll be right back. And welcome back to Tomorrow. Now, before we get into our interview segment, and I'm really excited for this one because I'm a huge advocate for next generation propulsion, I did want to give a huge shout out to all of the patrons of Tomorrow who've helped make this specific segment of this episode happen. These are the Tomorrow producers. These people have contributed $5 or more to this specific episode. If you'd like to find out how you can help crowdfund the shows of Tomorrow, head on over to patreon.com/TMRO. All right, it is my honor to introduce Dmitriy. We'll stay with Dmitriy. We just confirmed before the show how to pronounce his last name, and then I read it, and I can't do it anymore. Do it for me.
Tseliakhovich.
There we go. Thank you. We're going to bring Dmitriy on the air. Dmitriy is the CEO and CTO of Escape Dynamics Incorporated, who's working on some really cool next-generation propulsion systems. So, Dmitriy, welcome to Tomorrow, and thank you for taking time out of your Saturday.
Yeah, thanks a lot for inviting me, guys.
So tell me, what is Escape Dynamics doing?
So what we're doing, we're developing the next generation propulsion technologies. The company is focused on building a reusable single stage to orbit spaceplane. And to get us to this point, to accomplish the mission, we are developing all core technologies behind external propulsion. So behind the propulsion technology that allows reusability and allows a single stage to orbit systems. So our focus right now as the company is on development of propulsion system, development of wireless energy transfer system that powers the vehicle, and development of all key components. So antennas, tracking systems, and microwave generators that actually can power the vehicle from the ground. I can go more into the details of the propulsion concept, or the way you guys want it. Basically, just I can either keep talking, or you can
Well,
jump in with the question.
Yeah. Let me back you up. So, there's a lot there, right? You got single stage orbit. You're developing the vehicle. You're doing ground-based propulsion, which is a term that we haven't really used here on the show before. But before we get into any of that, let's talk about existing chemical rockets and why do we need to do anything else, right? We've done chemical rockets since the 50s and earlier. They've served us well. Why not just use chemical rockets?
Right. Well, the key challenge is we see that today space access is unfortunately not as affordable, not as efficient, and certainly not as routine as anyone would want it to be. So if you look across the costs of the space access, it costs for heavy payloads $4,000 per kilogram with SpaceX, and for small payloads, for companies that want to ship small satellites into orbit, it very often costs north of $25,000, and that's very expensive, and it's also risky. So we see that it is very, there is a high likelihood that the payload will be lost. Even if the payload is insured, it still delays startups or companies working on building those payloads and deploying them into orbit. It takes them time and a significant lost opportunity if the payload is lost on the chemical rocket. So, and today the average is about 4% of payloads fail to reach either desired orbit, or there is an explosion on the during the launch. So there is still significant risk. There is significant cost, and and so that's what prevents us, frankly, from exploring space, from accessing space in a much broader and more intense and more fruitful way than we can today. So the technology, fundamentally, the issue is the fact that chemical rockets are inefficient. If you look at the actual rocket, only about 2% of it is useful payload, and the breakdown between the propellant and the structure plus payload is about 90-10. And this is fundamentally driven by the inefficiency of chemical propulsion. So we measure the efficiency of a rocket typically in specific impulse. You can think about it as MPG for cars, right? Chemical rockets got a fixed limit to their efficiency. The most efficient chemical engine is hydrogen, liquid hydrogen, liquid oxygen, and it amounts to about 460-ish seconds of specific impulse, which is driven by the fact that you can only store so much energy per kilogram of payload, per kilogram of propellant, so LOX and hydrogen. If you go to less efficient propellants, you will be less efficient. And for example, most of the rockets fly with 340, 350 seconds of ISP. And when you are in this domain, what happens is you cannot fly single stage to orbit, and your propellant to useful structure ratio is about 90-10. So this limit in ISP gives us what we have today, chemical rockets. And we see that we need multiple stage. It is still risky. It is still expensive. The question we ask at Escape is, can we do better? Can we build a system with substantially higher ISP, 5 to 10 times higher, or at least 2 times higher? And the answer is yes, but we need to move beyond chemical rockets. And so this is what we started to explore. We started to look into multiple concepts that actually allow us fundamental shift in efficiency from the limit of 460 to something substantially beyond. And the concept that we proved to be both financially and physically and engineering-wise viable is external propulsion, where we do not carry energy on board of the vehicle, but rather beam energy from the ground to the vehicle. So the shift in specific impulse for this concept goes from 460 for chemical to above 750 seconds for the first generation of the thrusters we're developing. And the key of what this allows is it allows us to go from 90-10 split to about 70-30 split. And so when you have 30% of your mass fraction to play with, that's where you can introduce more structure. That's where you can do substantially more in terms of the design, and that's what allows reusability and a single stage to orbit space access. So those are the two things that reusability, affordable, reliable reusability, and SSTO is something that obscenely hard with chemical rockets, and something that becomes possible or much easier with concepts which allow for ISP above, say, 600 seconds. And external propulsion is one of those concepts.
So I think there's a lot of information to digest there, and you've got a pretty unique system. I think the easiest way to explain this is to show everyone. You've got a nice animation. Why don't you tell us what we're looking at inside of this animation of your system design?
Let's do it. So we basically taxi the small vehicle to the launch pad, empty, without hydrogen. Then we lift it with the gantry and fill the system with hydrogen before the takeoff. This is the first phased array. Around 600 microwave antenna elements, beaming around 200 megawatt of power. So not obscenely a lot, but enough energy to launch something into orbit, so 200 megawatt. And the vehicle is absorbing the microwave with the heat exchanger on the belly of the vehicle. And this energy is basically heating the heat exchanger while the vehicle is flying. So this is the booster array, which accelerates the vehicle, which provides enough energy for the vehicle to accelerate to orbital velocity and tracks the vehicle throughout its ascent. The energy is converted into thrust via the heat exchanger. So the microwaves are heating the heat exchanger, ceramic matrix composite heat exchanger, and hydrogen is flowing through this heat exchanger to be converted into thrust. That's the principle of operation. Our goal is to deploy small satellites. So we're targeting small vehicles with initially up to 200 kilogram payload. We deploy the satellite, and then the goal is to return the vehicle after one orbit, to return it back to the spaceport. So it's a very small deorbit burn. We need, because we fly LEO, we only need about 0.1 kilometers a second to deorbit, and then the vehicle would land and eventually get prepared for the next flight. So this is the concept of operation. Power the vehicle wirelessly, deploy the satellite, come back to orbit, be ready to fly again.
So in this system, you mentioned it's ground-based propulsion. It's those microwaves from the ground essentially beaming up and then superheating the liquid hydrogen. Will you need ground stations around the Earth then to send those microwave signals up to the vehicle as it goes around the Earth in low Earth orbit?
So if our goal, as it is, to only launch into circular trajectory, into circular orbit and deploy the satellite, then the answer is no. We need only 2 arrays, and we basically designed the entire launch to be able to accomplish orbital acceleration to 7.8 kilometers a second with 2 arrays only. And those 2 arrays are physically separated by around 200 kilometers. So you can imagine one station in one part of New Mexico and another station in the other part of New Mexico, or any take other state. But basically, we only need 2 arrays to reach orbital velocity, and this is exactly our goal. We want to develop and deploy an extremely affordable and simple to operate means of getting into LEO, not necessarily to transport things in orbit, but to get affordably into LEO. If or when we are successful with putting payloads into orbit at, say, a few $100s per kilogram, then it becomes a different challenge and a much, I would say, easier challenge to transport things between orbits and to basically operate the in-orbit infrastructure where we tug things with ion engines or with any form of different propulsion to a desired orbit or desired trajectory, or even into Earth escape trajectories. But our goal is specifically to put a vehicle into, say, 350 circular orbit around Earth.
Is that why you're not looking into space-based microwave beamers at all?
So of complexity of everything. So building, it's important to realize that building a system like this is obscenely hard. It just takes a lot of time, a lot of effort, and we need to focus on the fastest path to making something useful to the world, to the customers. And the first and foremost thing that we can build is the vehicle that flies into orbit, powered with two smallest possible arrays, smallest vehicle, smallest array, delivering payloads into orbit. In the future, yes, this concept, the concept of wireless energy, it's applicable to many things. It's applicable for in-space propulsion. It's certainly applicable to powering things from orbit back to the ground, for example, on the surface of Mars or on the surface of the Moon. Yes, there is a huge amount of applications of wireless power that can come later in the game. But in order for all of this to happen, we need to first build something useful to customers and something useful to the world, so that this concept get a chance to grow and evolve.
Speaking of building, you actually have built some stuff. We have another video. It starts off with an animation, I believe, that shows some of the stuff that you've built. Can you walk us through a little bit of what we're looking at here?
Absolutely, yeah. And the animation is primarily because the microwaves are invisible, and here we're showing them in the basically red light. So this is the gyrotron that we designed and built, and the microwaves are beamed through a system of mirrors and then go from the main reflector to the thruster. And this is the very first generation of thruster that we used to heat. So this is the IR image where the microwaves are hitting the heat exchanger. This is the optical video of the same process. We're basically heating remotely from about 4.5 meters silicon carbide heat exchangers through which we're flowing gas, creating thrust. And this is an exciting result that we recently accomplished. This is specific impulse as a function of time. And so what you see here is that we, in our thrust tests, we reached above 500 seconds ISP using helium as the propellant. And helium is not the actual propellant we plan to use. The actual propellant is hydrogen. If we used hydrogen instead of helium in this test, what we would see is specific impulse above 700 seconds. Certainly above 600 seconds, which is close to the requirement of reaching single stage to orbit. And that was our goal with the first generation of thrusters. We wanted to show that we can build so efficient thruster that we almost guaranteed to have SSTO and open doors to reusability and future remarkable applications. And that's what we've accomplished so far. We designed and built a gyrotron, which is the microwave emitter, which generates continuous microwave output in millimeter waves. We designed and built a really awesome system of optics that allow us to beam those microwaves across distances. In our case, we're limited by the size of our hangar, but overall those distances can be much larger, obviously. And right now, we're beaming this power to thrusters, and generating thrust, and at the same time, we're testing how we would beam this energy to flying vehicles, so that we know we can reliably deliver energy to something that flies and track the vehicle as it flies. I think there is a video that we can also show of the antenna that we built. So this is the gimbaled antenna, and you can see how smooth and fast the tracking algorithms work. It's a fully autonomous algorithm that tracks basically a UAV. In this case, we do only the localization and tracking. This is one of the first experiments we did, so no energy uplink yet. And basically, we designed tracking algorithms. We designed optics that allows microwaves to propagate and be beamed. And this is the first low energy uplink experiment where, so what you see on the bottom of the UAV is an array of LEDs that output power proportional to the amount of microwaves that are actually reaching the receiver on this UAV. It's not yet powered with microwaves, primarily because we're not beaming high power in the lab outside of the enclosure. So all of the engine test is done in the enclosure so that microwaves do not propagate into the lab, and the low power is done with the quadcopter experiments. So designing and developing those system has been what the company has been doing so far. Is proving step by step that each component of the process is possible, and that's what we basically that's what we did. We took the energy from the grid. The energy comes from the electric grid, is converted into microwaves in the gyrotron. It's beamed through a system of mirrors. It reaches the thruster, and it is converted into actual measurable thrust and very efficient thrust for that matter. So that's basically what we've accomplished so far. And right now we're scaling our hardware systems up for much bigger demonstrations and eventually for flight demonstrations.
Someone asked earlier, and I apologize, I don't remember who it was in the chat room, but they asked, what can you scale this to, right? So you're doing small demonstrations now. I assume it's kilowatts of power, not megawatts.
Yeah, tens of kilowatts, yes. So we're beaming tens of kilowatts of power to the thruster. For the next step, we're planning to scale the system to megawatt level and test a much bigger engine, basically the engine that can go on a small UAV and power the small UAV during flight. Megawatt is already a pretty significant amount of power. It's more than has been ever wirelessly transferred for the use of propulsion. So this is our next milestone. We're planning to take it to the outside facility and do outdoors demonstration at a megawatt scale. Before that, we will be doing outdoor demonstrations with tens and hundreds of kilowatts, obviously. But the long-term scalability of the system is we need about 200 megawatt to put 200 kilogram of payload into orbit. And from there, after we are successful launching 200 kilowatt and 200 kilogram satellites and deploying payloads on the order of 200 kilogram, that's where we can start scaling the vehicle up. And realistically, we can see the system scaling from 200 kg payload to about 1,000 kilogram payload. From there, most of the customer base that we foresee will be covered, and most of the needs that will be addressed. And the rest of the system, the rest of the heavy lifters will do the rest of the job. SpaceX is doing phenomenal work, world-changing work in building large launchers that will be able to deploy large-scale infrastructure into orbit. Our system with up to 1,000 kilograms of payload will be able to basically provide the other end of this game and to provide reliable, on-demand, fast transportation where you can basically park your spaceplane in the hangar, fly whenever you need, and come back. And so that's the alternative mode of SpaceX that probably does not require much more than 1,000 kilogram of payload per flight. So yeah,
go ahead.
So in the summary, we see the system scaling pretty easily to 1,000 kilograms of payload.
What are the differences? I mean, you mentioned a little bit. SpaceX does the big, huge launchers. You're going to, I assume, focus on nanosats, microsats, those smaller guys that just really aren't covered by any launch providers today. Is that kind of your target market?
Oh, this certainly is, and we see this as a huge market potential. So the way I think about it, if you think today for companies like Planet Labs and others, to put a small payload, a small satellite into orbit, it very often costs north of $25,000 per kilogram. That's a lot of cash, and it's very expensive. And they also have to wait for a long time, frankly, before their payloads can even get a shared ride. At the same time, there is an opposite dynamic, is that the demand for those satellites is growing exponentially. And the reason why it exhibits this is because those satellites, they are designed to produce data, and they are designed to basically expand our civilization's exponential growth in that data demand, internet demand, video, and basically digital economy. So there is this economic force that drives the demand on small satellites. Think about what we see today with Planet Labs providing pictures live to customers, and they are covering very tiny fraction of the potential market. they would benefit from launching thousands and thousands of those satellites. And the same is true for providing internet from orbit. There are 3 billion people that will gain internet access over the next several years from the satellites that will be deployed in orbit. Those satellites can be launched in a big cargo ship if you launch, let's say, 1,000 of them. But they will need replacement, and replacing them, it's much easier if you can just fly, deploy your satellite, and come back and don't worry about that. So this market, this exponential growth in market demand for data, for internet, for video, that's what we see as our customer base in 5 years from now, when we plan on flying the payloads into LEO.
How do you expect this will compare with other small launchers like Firefly Space Systems in terms of cost and efficiency wise?
Right. So the system that we're building is obviously, as you've seen, fundamentally different. It does not use chemical combustion, so it's not limited to multi-stage systems with very small fraction of payload. If we look at the quotes, without going into specific providers today, even those who are not flying but are planning on deploying, on starting to fly small rockets, their costs are still north of 25,000 per kilogram for small launchers. So there are great companies that are innovating in small launcher chemical, but still they are their prices, even their projected prices, which may not be met, they are high. They're much higher than, for example, per kilogram price of SpaceX launching heavy payloads. And so, but the fundamental, I think the fundamental difference is profoundly the technology. It is possible to build something that will fly like an airplane into orbit, and that's what we are doing. I think that's the most important part to distinguish about us, is we are looking at what's next, what's the next generation of propulsion, and we want to build that, something that will allow things that are not possible with chemical rockets that Firefly or other companies are building. And this is basically the plane type of aircraft-like operation into orbit. It requires innovation on the propulsion side. That's what distinguishes us primarily.
Well, we've seen aircraft-like craft going into orbit before with things like the space shuttle. But I think one of the big differentiators here is that with traditional rockets, you use them, you throw them in the ocean, you're done. With the space shuttle, you refurbished it. It wasn't reusable, it was refurbishable. But you're talking about rapid reusability, and you're likening yourself to an airplane. What is that rapid reusability? You know, an airplane you can fly multiple times per day. Can you do that? How quickly can you turn it?
Certainly, this is the plan. I mean, and let me elaborate on this analogy with airplanes. If you think about why airplanes are reusable, the answer is that the engines are so much more efficient. They don't fly into orbit, so their engines are efficient for what they do. But fundamentally, fraction of propellant on the aircraft, on the airplane, is about 40%. 60% is useful structure and payload, people, passengers. So the split is 60-40. On chemical rockets, the split is 90-10. 90% propellant, 10% useful. That's why rockets are, and the same was true for space shuttle. Only about 10% of it was structured. That's why it took so many man hours, such long time, and so much money to refurbish the vehicle after every launch, because it was operating on the margins of what's possible, the structural margins. That basically complicates through cyclic fatigue, through all of the issues that you have to worry about when the hardware is flying into space. Unless you can increase the fraction of structure and use on the vehicle, it is really hard to do rapid reusability. So we want to shift the game closer to the airplane-like fraction. It will not start at 40-60. 40% propellant, 60% useful, like on airplanes, but it will start at 70-30, which is much, much better than what we've got today. And this additional percentage of structure can allow us to basically have rapid reusability. You land, you inspect your vehicle, and you potentially could fly again. Or in our at least initial operation, we're thinking more like we'll have several vehicles and we will be flying every third day the same vehicle, with just giving it time to to get inspected, and if something needs to be patched, well, it will be patched. Initially, obviously, as with any new technology, it will not be immediate. There will be time big learning curves where we will, between the first flight and the time when we can fly the vehicle 50 times without repair. But I think it is fundamentally possible to fly a vehicle like ours for 50 times, maybe with small inspections in between those times, and then do a major retrofit and fly again. So fundamentally, yes, we are trying to build a rapidly reusable spaceplane.
So I'm watching the TMRO chat room, and there's a lot of talk right now about the microwave beam itself and how focused it needs to be, and tracking that vehicle. So we saw earlier video of you already tracking a drone very smoothly, by the way. That's actually quite hard to do. So kudos for that. But then how focused do you have to make that beam, and how precise does that tracking have to be to hit that vehicle?
So the precision needs to be pretty tight. I mean, we need to focus 200 megawatts into a 10 meter square, so 3 by 3 meter vehicle. It needs to be precise. The second part of your question is the power density and focusing. We accomplished this high energy density on the vehicle through a phased array. So if you think about the actual size of the booster array, for example, it is close to a kilometer by kilometer on the ground. So imagine a solar farm. It's about the same size as a large solar farm. And the energy density close to the ground is actually not all that high. The average energy density over a square kilometer is actually not much bigger than the solar. It may be several times the solar power density. But when the beams converge and adds up coherently at the vehicle, that's where the coherent interference basically, and the phased array power beaming gives us this focus, gives us the energy convergence to very high power. So the energy density at the ground is reasonably low. The energy density of the vehicle is high. In terms of the tracking precision, the vehicle is moving very fast, obviously, when it's in orbit, but it also is moving very far away. So the angular speed, the slew rate of antennas, is actually not all that high. It's lower than what's routinely done with many of the radar system deployed today. So we do need to steer the beam. We can accomplish tracking and steering with two independent ways of controlling antennas. One is mechanically steering the big dishes, so they basically track the vehicle as they move. But another one is adjusting phases of the microwaves emanating from each antenna, so that we can have a very precise, up to a meter precision steering with just a phase adjustment of antenna. So it's basically phase steering of the phased array. And that's the phased array power beaming is what allows a safe power beaming, because the energy density on the ground is not all that high. But also it allows precise power beaming, because we can steer the beam very carefully at the vehicle. So the way we plan to accomplish this, it's possible to track the vehicle. We do this with airplanes. We do this with rockets today. So there are multiple ways you can determine where the vehicle is on the sky. We've got a very strong prior into the statistical model. We know that the trajectory. So the trajectory is predicted, and you also can see the vehicle with the IR camera, because the engine is glowing hot. You can also see the vehicle from the beacon on this vehicle. And if you combine all of those data sources that provide you the coordinates, you can basically build a very reliable model of where your vehicle is at any given microsecond. That will eventually allow very precise tracking and power beaming to that vehicle. And I think the last thing it's important to say, it is by no means an easy problem. So yes, we know how to do this in theory, and most of those components have been demonstrated in independent experiments. We did some demonstrations with small antennas and beaming power to localizing, tracking a quadcopter. From here to the actual launch, there's a huge amount of work that needs to be done, and there will be questions that we will encounter that are really harder than we think right now. But we know that the physics, the fundamentals are there. And so what lies between the fundamentals, what we've done so far, and the real launch system is, well, hard engineering and execution. And that's why we're building the world-class team and solving those problems every day.
Let's talk about that world-class team. We actually have a picture of some of your team, I think, right here. Who do you have some of the people working on this project right now?
Right, so one of the most remarkable things about space exploration, about escape, specifically focusing on the unique challenges on building the next generation, is this bold mission, and this challenge attracts amazing people. I've been blessed in my life to go to Caltech as the grad school, and so several of the people on the team are Caltech grads, Caltech Ph.D.s. I also spent time at MIT, and part of the team is from MIT. The founding team. So one of the people in the middle of this image is Richard Shaden, the person who I met as a PhD student at Caltech, and he's been searching at that time for a way to dramatically change the way we fly, to basically enable sustainable travel in the atmosphere and beyond. And I was thinking about I've been through all my life, I've been passionate about building the future generation of propulsion systems. And when Richard met, we immediately resonated. And he is a very successful entrepreneur and lawyer. And he's also extremely passionate about aviation. He's been flying his own planes for the better part of the last 50 years. So he flies a lot, and he flies himself. He invested in the company and has been building the company with as the founder and as the part of the team from the very start. Another person to mention whose importance has been phenomenal to the team is Letitia Garriott, who joined as the business development person and as the president, and has been helping to form our founding vision and make the company grow and expand to its full potential. But everyone on the team, as you can see, it's a pretty small team right now. Everyone on the team is just being a blessing to work with the people who have the tremendous brain power, execution capability. We've got probably the best machinist I've ever seen in my life, who can manufacture things with precision that just unfathomable for me as a physicist. when I see people actually building hardware with that level of precision, it's just remarkable to me. It's what makes the ideas actually work. So yeah, that's I cannot be more privileged and honored to be working with that team.
And where can people go for more information on what you're doing, like Twitter accounts, social media, stuff like that?
Yeah, I mean, we do have a webpage where we talk about what we build and show pictures. It's escapedynamics.com. We also share updates reasonably regularly through our Twitter account at Escape Dynamics and through our Facebook and LinkedIn accounts. We try, especially after we started to do those hardware demonstrations, we try to keep people who follow us in the loop on this, and also we are part of the Singularity University network of companies. SU has been a big part of my personal development and growth, and so through Singularity University channels, we very often share the information about who we are, about our progress, about our vision for the future.
Dmitry, this is really exciting stuff. Like I said, for anyone who watches the show, I'm a huge advocate for next generation propulsion, not just in space, because we got a ton of people doing stuff in space, but getting off the planet as well, because it's such a hard thing to get out of our gravity well.
It
and
is.
Bringing all that fuel up with you, you look at the cost of a rocket, and while the cost of the fuel itself is a small part of the rocket, when you take into account all the systems and the tankage and the ground systems and all the stuff that goes into the fuel, almost none of it's the payload. It's all related around fuel somehow, and fixing that problem is going to be key to opening up that final frontier, and I'm excited that you guys are working on something for that.
Thank you so much.
So, all right, you've actually offered to come back during After Dark, so we're going to take you up on that. So we're going to take a quick break and come back with some viewer comments, and then after that, we'll answer some more viewer questions in After Dark. Stay tuned. We'll be right back.
Thank you.
And welcome back to Tomorrow. I do like that song. That's fun. Now, before we get into comments from our last show, I almost said last week's show. What? I was dancing. I boogie every time. Do I not dance every time that firewalking thing comes on?
Yes, you do.
Every single time.
We all do.
Yeah, I do the little...
Yeah, but you know that's the wrong commercial break.
Oh, was it?
Yeah. So it's the commercial break right before the second segment.
No, we're airing it that way. That aired correct.
Nope.
We're flipping them.
Now we're in the third segment.
Oh.
You just broke the magic, Ben.
I broke the magic.
I was
bring up
try
Mike's
to
mic.
ignore it.
Bring up Mike's mic. What was Mike going to say?
If we're nitpicking here, earlier when we started the first segment with space news and everything, you said thank you to all the premiere members and showed the producer members.
Yeah, I'm
That
gonna
was-
that's why I
we can
stumbled.
put the producer part in.
That was bad.
Yeah,
premiere
that's why I
Okay, just
stumbled.
making sure you caught that.
You know what's great is I'm actually not going to edit this out of the show.
No, so
we're going to
everyone
leave it
watching it is
exactly
gonna
as
be
is.
totally
and now you're
confused.
going to know that we shoot these out of order.
This
All
is
right.
why you have to watch live.
Thank you to all of our Patreon Plus subscribers who have helped make this specific segment of, you know what, Exploding Kitten, right there, Exploding Kitten. This episode happened. These are the people who've contributed $2.50 or more to this specific episode. But wait, and actually, everyone here, when we come back with After Dark, we bring Dmitriy back. You're going to get instant access to that as soon as we post it online. But wait, there's more. If you can't afford $250,
Wow.
who can? If you can't afford $2.50 and you don't think the show's worth $2.50 per episode, maybe it's only worth $1, maybe it's only worth 50 cents, maybe it's only worth 1 penny, you can still get your name in the show. That's right, we have our patron subscribers. These are people who contributed 1 penny up to $2.49 to help fund this show. We are primarily a crowd-funded show. Every single penny helps. Thank you to everyone on the screen to helping to make this show continue to happen. All right, let's go ahead and get started with some comments from our last show. This was a couple weeks ago. This was talking about what are the missing steps in human... Hello, Mike. What are the missing steps in human spaceflight? The show just derailed. We started strong, and we ended like this. Go ahead, Carrie Ann.
This one comes from Streetwind off of Reddit. In regards to X-Core,
Dmitri's not coming back, by the way. He's like, no, I'm out.
No.
I'm out.
yes, in regards to X-Core increasing prices to $150K, I think they're doing it to keep the backlog smaller. I mean, 300 tickets sold already. The first test flight of the qualification plane, which will never even fly customers, is still a year out. If I were X-Core, I'd want to say, hey, let's not get ahead of ourselves quite so much. Their main competitor kind of did, and all it got them was a reputation for endless delays.
I think those are two different things, though, right? I mean, promising things that you don't keep and then setting a ticket price are not the same thing. So X-Core has not said we're going to fly humans at X time. They're basically like, look, we're working on it. We'll get to it when we get to it.
I see what he's saying, though.
I guess. I do. I still, I'm. If we're to open this frontier, then we need companies like Escape. We need companies like Xcore and Virgin Galactic to work on lowering those prices any way they can, not raising them up. So yeah, there you go. That's what I said last time. I get your point, but anything they can do to lower the price would be good. I know they're a business and need to make money, but if we open this frontier, there will be so much more money to be had by opening it up than by keeping it closed and highly restrictively high cost, in my humble opinion. All right, next up.
This one comes from Jimmy Turpin off of Facebook, actually. Hi, I just watched season 8, episode 8, and I've been watching your show for about 6 months now. Hi, Jimmy. I downloaded the app that you spoke of on your show, and I've been trying to get my nieces and nephews interested in space. What would you suggest for apps when teaching children?
So first off, Jimmy, I'm sorry, because, season 8, episode 8, that was a while ago, and I just now brought it onto the show because it was buried in like a Facebook notification thing that I didn't know was there.
Yeah. And
also, everyone who just got a reply from me today, because I just found that Facebook notification thing that you sent me messages on. Sorry. Some of that stuff went back like a year. So there are actually, so first off, there's Launch Library, which is our own kind of, it's not really an app, but it's a database of launches. And if you're building apps and you want to bake into your app, like, hey, here are some upcoming launches, you can use Launch Library for free, our API, to just cook it right into your app. And now you've got a list of all the upcoming launches and what's going on inside of space. That's really cool. Outside of that, you've got Mission Clock, which I think is a really great app. That's for iOS. You've got T-, which is on the Android app. That's also a really great app. You've got, Mike, do you remember what Eyes turned into, Google Sky turned into? Dada, do you remember?
I think it's Skyview now.
Yeah,
Oh, yeah.
That's a really great one as well, because you're looking up at night. All right, let me tell you my life. We're at Disneyland, in Tomorrowland, waiting in line to go on Space Mountain, as I'm sure everyone does. And we look up, and there's a really bright, kind of flickering star or speck of light in the sky. And we go, what's that? So Google Sky,
well, and
or
not all
whatever
of us
it's
can
called
carry,
now.
Our resident astronomer,
Jared, yeah.
Jared
would be like, well, if you do this with your hand, then you take into account this. That's obviously serious.
Yeah.
And we'd be like, I don't know how you did that.
Jared knows all that stuff, and it was really amazing to watch him in action.
Actually, ironically, that also happened in line at Disneyland
Pretty
in
much,
Space
yeah.
Mountain. That's exactly what happened there. Otherwise, I normally take my Google Sky and I kind of look at it. It's really nice. You look up and it's like, oh, hey, there's Orion. There's there's the moon. Thanks, Google Sky. So whatever that's called. So I think actually, if you guys know of some really great space apps for Android, iOS, or Windows Phone, if anyone owns one, leave those in your comment. Had to slide in there. Leave those in the comments, and then maybe we can all kind of benefit from that. Or leave a Reddit post, maybe create a Reddit post talking about really cool, spacey, geeky apps. So there you go. All right.
I'm sorry, quick correction. The Google Sky app is simply called Google Sky Map now.
Okay, Google
Not
Sky
Skyview.
Map. Thank you, Phantom Voice. Yeah. All right, next up.
This one comes from Hornhoof Records off of Twitter.
Hornhoof Records.
Hornhoof.
It's hard to say. Hornhoof Records.
What's missing? Radiation shielding. There was a company creating a shield that created a magnetic field around a craft.
Yeah, actually, so this is
sounds
in
awesome.
reference to, again, our last show, what's missing to get humans onto Mars. And radiation is a nasty problem in space. And the way it works in Earth is we've got a giant magma core that spins and creates a magnetosphere, so that we've got a magnetic shield from the harmful radiation of space. Mm-hmm. Well, what if you magnetized your hull? Kind of, all Star Trek style. And so I remember the same thing. There is a company working on that. I think it's a really great thing. Otherwise, you can use water, but it's very, very heavy. Mm-hmm. But there are other methods to take care of that. Or you can just get there really fast, right? That's another method is, again, propulsion, changing the propulsion and just speeding up the trip, not taking 9 months, taking a month, taking, a few days. I don't know. That would be...
Stargate.
Start using a Stargate. using a Stargate. Just, we got one in Antarctica. Just go unbury it. Off you go.
No problem.
So there you go. All right, next up.
This one comes from Grumpy Space, also off of Twitter.
Also, by the way, the name doesn't match. No, go back. The name does not match the icon on this one.
He's only grumpy about space.
Oh, apparently he looks so happy.
Otherwise,
but his username is
such a
Grumpy
teddy
Space.
bear.
He's right. I mean, he's like super happy and thrilled to be tweeting, but his name is Grumpy Space. All right.
In one of your last After Dark videos, you commented, you commanded your Amazon Echo to do something, and mine tried to do it.
Alexa,
LOL.
Alexa, tell me a joke.
What kind of key did the American colonists thirst for? Liberty.
There you
What
go.
kind of key do the American colonists thirst for?
Liberty.
Liberty.
Alexa, tell me a joke.
No, don't do that.
Knock, knock. Who's there? Isabel. Isabel who? Isabel not working? Times before I started knocking.
That part was good. Okay.
All right, next up.
Anyhow.
You're welcome, Amazon Echo owners. You're welcome.
James Harkness, off of YouTube.
So James has not. This is not James' first rodeo. I don't know. Keep going.
Says,
I made that even more awkward.
yeah, you did. New data shows that it, in fact, to be 90% cheaper to colonize the moon than initially thought. I'd love to hear your moon colonization mission announced first thing when I wake up tomorrow due to this revelation, please.
No kidding. Absolutely. If it's going to be that much cheaper, if that's real. I have a hard time with it a little bit because, it is really, really hard to do. But yeah. Where are the moon colonization plans? Come on, ULA. Oh, it's not
I would
really
like to
ULA's
take
plan.
this opportunity to announce that Space Mike Enterprises is going to be colonizing the moon, and our deadline is 2057.
2057. All right, that's great. No, but really, we should work with speed and energy towards colonizing the moon and Mars and going to Europa and going other really cool places. I'm not sure you'd want to colonize Europa. Maybe turn it into like a cleansing bath area, or what's it when you jump into the frozen lake? What's that called?
Oh, like a polar plunge?
Polar plunge. Yeah, Europa polar plunge. That's what you need to do. All
For a
right.
second, I thought you were talking about the Prince song and talking about jumping into the cleansing waters of Lake
With
Minnetonka. Yeah.
Oh man.
Oh, I'm so confused. All right, so this last comment comes from Juxtapose Stars.
We've lost all viewers
apparently
by this point. Yeah.
off of YouTube. Says the real missing links: reproduction and dealing with gravity. If humans cannot successfully reproduce in stronger or weaker gravity, any mission is a temporary one.
All right, any volunteers? We need people to volunteer to help with replication in space.
Do I have to keep the child?
Well, this got very awkward very quickly. All right. On that note, I'd like to thank everyone so much for watching. Now that we're back, we're going to go ahead and take another week off. We're not going to be here next Saturday. I'm sorry, but we will be returning the week after that. So I hope everyone enjoyed the interview. If you're watching live, stay tuned. After Dark is up next. If you're a Patreon Plus subscriber, After Dark will be available to you imminently. Otherwise, everyone else, it should be available in about weeks. Thank you so much for watching. See you in 2 weeks.